In the last video, we introduced the light wave and also talked a bit about index of refraction for a material. Here now I'm going to go double back and take a look at the wave nature of light. Remember, historically, there was a debate between particle and wave nature over a couple of centuries. Eventually, the scientific community settled out onto the wave nature, except that we had to modify that in the 20th century to talk about wave-particle duality, but that's for much later. So building off of the idea of, say, a water wave or something like that, since Christian Huygens, who was thinking about light as a wave, was trying to figure out how the heck could this propagate. He didn't know what the light wave was. We know that it's an electromagnetic wave, and we will work out how that works later. But he was just trying to think, how can light propagate at all? And he got to thinking, let's say, if I were to have a water, say this is a wave front. If this were water, what you could imagine is if this was the crest of a water wave here. In a certain sense, mechanically speaking, as far as the pool of water is concerned, all that water that's sitting above the crest, you could get rid of that and just replace that with like a giant string of pebbles and let all the pebbles drop at once, since the water is bobbing up and down. So Huygens reasoned that if I were to look at, say, some wavefront like this, every point on the wavefront, and I'm just going to draw a few points, okay, quite a few, but still, every point on the wavefront is a source of what get called wavelets. And these wavelets are spherical waves. So the idea is that I'm only going to draw in the wavelets from going forward here. So at this point here, at some time later, the wavelet would have propagated there, and that same time this one there, that one there, that one there, that one there, that one there, and so forth. And the idea here, let's fix my bad art on that one. Something like that. And the idea is that these wavelets will all constructively interfere to make the next wavefront. Now, these wavelets are propagating backwards as well. It is way beyond the treatment that we're doing here. With very tedious math, you can show that the wavelets all destructively interfered themselves out, and so light doesn't propagate backwards, it just propagates forwards. But the idea is that we can then repeat this game again. Every point here on the new wavefront will be a source of wavelets, and those wavelets will propagate forward and constructively interfere to make the next one, and so forth. And that is how Huygens reasons that a wave is propagating. So for a plane wave, here's a plane wave. Plane wave, each wavefront that you make will be another plane. Now, we can also have what are called spherical waves. We saw those when we were treating sound, and we were thinking, say, about sound coming off of a subwoofer or something like that. With a spherical wave, it's the same kind of idea, but with even sketchier artwork, I'm afraid. I'm just going to go ahead and go straight to the punchline here, because otherwise I'm not going to get this look good. There we go. So again, here we can pick, there we go. So pick a whole bunch of points on our spherical wavefront here. And they will all propagate out waves to constructively interfere to make the next wavefront. And that will be expanding out in all directions. So, oops, there we go. Yeah, something like that. So this is a spherical wave. And with plane waves and spherical waves, a plane wave will, the next wavefront made will also be a plane wave. With a spherical wave, the next wavefront made will be a spherical wave. With anything else, it's not going to look identical in shape to the thing that made it. But these two turn out to handle a lot of the cases that we worry about. Okay, so this is how Young is reasoning that this is working. He doesn't know exactly how it's working, but he's saying, hey, somehow every point on the wavefront here propagates out these little wavelets. Basically, each thing is acting as a little point source, emitting light uniformly in all directions. He does the tedious math to show that that all destructively interferes in the back, so the light has to propagate forward or propagate outward. And he gets that this wavefront, that the wavelets will constructively interfere to make the next wavefront and then the next and so forth. Same with the spherical waves. Well, that's great, but how the heck do you test that? And to that's going to fall to a fellow by the name of Young. And Young is a person who definitely got around. This is the same Young as in Young's modulus for materials. And it's also the same Young who proposed that, at least in the case of foreign loanword names, that Egyptian hieroglyphics could, at least in some cases, represent sound values. It turns out that it does represent sound values, but Young was the first person to propose that too, so he's definitely one of those folks who got around a lot. Anyway, this is actually something that you can do at home. To do this, you need a piece of aluminum foil and an X-Acto knife and probably some styrofoam or something to help you make a couple of clean cuts. And what Young did is this is basically what he did. So you take your piece of aluminum foil and you X-Acto in two very closely spaced, as close as you can get, basically. He X-Actoed in two very closely spaced parallel cuts. Now, obviously, now if you go and decide to make this, take care of yourself handling the X-Acto knife. But you can look through the two slits at a light source. And this light source, please do not make it the sun. You stare at the sun long enough and you will not have vision left in that eye. But say you can look through these slits at light, just a light bulb or something like that. And if you look through it, what you'll see is a not very good spectrum. Okay. But, if you do it right, you'll at least see some colors spread out. All right. So if we take a bit more of a top-down view, So here now we're looking down on top, and what I'm doing is this is our material and greatly exaggerated. These are 2 slits here. So what you made with the X-Acto knife. Now if you're really if you're trying to be very precise about this, you'll use some sort of light source that is pretty much all of one wavelength, if you can make that happen. You didn't have that when you used this, that's why you got a rainbow. But you pick a single wavelength of light. You try to make it at least reasonably a plane wave coming in. And then the idea is, remember, every point on the wave will act as a source of wavelets. Well, what about these 2 points right here? So here and here. Let me do this in a different color to maybe help make it a little easier to see. So if we take a look at the light that makes it in this slit here and this slit here. Now, because these are long slits, the way this is going to interfere is, as long as we stay kind of in the middle, top bottom of the slits, the wavefronts that we get will look roughly like cylinders. So we'll get these cylindrical wavefronts propagating out. From this one, but then also from this one. And you'll remember when we did this with sound, wherever you have crest meets crest or trough meets trough, you're going to have constructive interference. And if you have a crest meet a trough, you'll have destructive interference. So if I were to, say, put a screen over here. Yeah, let's make that one black again. So let's say I put a screen over here. What I'm going to get is right at the center, the difference in distance between this source here and that source there is 0. It's the same if I'm right on the center line. So just like we saw for sound, this will be where we have constructive interference. So we'll call this the central maximum. And we're going to have it be bright, which I'm going to indicate by drawing like this. If I can do an okay job of it. Yeah, like that. So this is just going to be the brightness of the light. Like that. Now let's say I go over here or over there. These will correspond. Let's use, say, purple here. This, in this case, the bottom path is longer than the top path, or vice versa. The top path is longer than the bottom path by 1 wavelength. So this will be, if we are numbering these, we usually call this M. It's not mass, it's just a number. This is 0. And both of these would be M equals 1. And what M is telling us is by how many wavelengths do these path lengths differ. And this will also be a bright spot. Not quite as bright as the one in the center. So I'm trying to indicate it like that, but something like that. And then we can repeat it out here. You'll have M equals 2 and so forth going up. M equals 2 and so forth going down. And there's, you can have M go up to a lot. And similarly here, just to highlight this out here. This here will correspond, let's get a little more contrasty color. This here, there. No. There. This there, or there. Those are both dark spots. Or dark fringes. So we're going to see this, and this is where, say, at this point here or here, at this point here, the light coming from the bottom source took an extra half a wavelength to get to here than from the top source. So if the top source had a crest coming here at this exact moment, the bottom source would have been a trough because of the half wavelength difference. Or here it would be reversed, but again be the same deal. You'd have one crest, one trough, and they would more or less cancel out. So if you, to give you maybe a little more clarity of what I'm talking about here, this is a picture of the light projected on a screen from one of these setups here. The light is red, so a longer wavelength. Red tends to be longer red is longer wavelengths, blue is shorter wavelengths than the visible. And the rest of the spectrum in between. And you can see that brightest bit in the middle, that's the central maximum. And then as you go off, you can see that the fringes get dimmer and dimmer. If you follow it far enough out to the edges, you can see that there's a particular dark spot, and then you start to get the beginnings of another pattern. That's having to do with the fact that the slits themselves are not ideal, infinitesimally thin slits. We'll get into that effect later. That's a phenomenon known as single slit diffraction, which we'll get to in a different video. But just for the moment, what you can see is central max is the brightest, and then it gets dimmer as you fall off to the sides, but you can see that we have this nice even spacing. And it turns out that this spacing is what can help us figure out the wavelength. So this end. If we go and take a look at our setup here, what we have to understand is that in any practical experimental setup, I cannot, to scale, draw the two slits and the separation to the screen. I cannot do this to scale. These slits are usually, on the order of 1 millimeter or less apart. The screen is probably at least 0.5 meters away, something like that. So really, this distance here should be like 500 to 1,000 times bigger at a minimum. Proper lab setups, you'll make this even narrower. You'll make this even farther out. So you might have, a factor of 10,000 between this distance here and this distance here. And what I'm trying to get at is that effectively makes this distance to the screen, let's call it L. This is very large compared to the spacing of my two slits in my setup, which we call D. This is very small. Now, the problem that we're going to have here is that if I were to try to draw this to scale, if I'm going to try to draw it in this distorted scale, you're always going to get that, say, if I look at, say, I don't know, the third bright fringe or something like that. So just for argument's sake, if I draw it here at this bad scale, these lines don't converge, and the reality is they do converge, but this is so far away that if I just kind of focus on what's happening over here, these lines, they're heading in that direction. So here I'm trying to just indicate lots of distance here. That I'm not going to try to draw in between. These two work lines, from the upper slit and the lower slit to whichever fringe I'm interested in, these are almost parallel. Actually, I'm going to say that right here. In fact, the angle between them is very small indeed. They really are almost parallel. So to calculate this, what we'll do is we'll just assume they are parallel. So we'll treat them as if they're parallel. And by doing that, we can figure out the extra distance we had to go from the bottom one to the top by just dropping a perpendicular like this. So this is the extra distance. All right, so if the angle that basically either of these is going at is theta, which is the angle that we're making out to our m equal, to whichever fringe. I picked m equals 3 arbitrarily here. This angle here, you can work out the geometric construction, also has to be theta. All right, so then this extra distance here, that has to be equal to d, and so this here is d is the hypotenuse. This bit right here is the opposite, so this extra distance here is d sine theta, like that. And this has to be equal to however many extra wavelengths we traveled from, say, the lower versus the upper, or if we're down here, the other way around. So this also has to be equal to the number of extra wavelengths traveled times the wavelength. So this is true in general so far. And it's important to note that this is the wavelength in the in whatever medium we're traveling in. Now, if it's air, we can basically approximate that as the wavelength it would be if it were in a vacuum, because the index of refraction for air is just barely bigger than 1. Okay, so if I want to figure out the angle, the thing is that since the fringe spacing that you'll see on these screens is typically on the order of millimeters, and this is going to be like a ½ meter or something like this. Yeah, I could get this angle here. I mean, I can say that this angle is equal to, we'll call this the y of the mth fringe. It would be equal to the arctangent of ym over L, because this is the opposite and L is the adjacent. But it turns out that these angles are so small in a typical lab setup. So in a typical lab setup, We saw that if the angle is really small, we ran across this before in mechanics when we were worried about the pendulum. If we work in radians, we can say that sine theta is approximately theta itself in radians. And if you don't believe me, you can just do things like, say, take 0.1 radian, put your calculator in radians mode, ask for the sine of 0.1 radians. You'll get back a number that's just barely under 0.1. Not enough to write home about usually. And it's not as good of an approximation as is for sine, but again, if angles are really small, we also end up getting that tangent of theta is approximately theta, again in radians. Now the difference here is that often you can go out to like 20 degrees or something like that with the sine theta thing. Tangent theta, maybe more like 5-10 degrees, something like that. So it's a smaller maximum angle where you start to worry about whether the approximation is good enough or not. But here these angles are typically going to be, a degree or less. So it's all good, and we can say that sine theta is approximately theta. So what that means is that we can take our d sine theta equals m lambda. I can rearrange that, get sine theta is equal to m lambda over d, and then say which that's true in general, but for typical lab setups, it's very well approximated by just replacing the sine theta with the theta and getting that that's equal to m lambda over d. And by the same token, remember we were saying that the tangent of theta was equal to ym over L, where L is the distance out to the screen. If I wanted to locate these, I can say, well, the tangent of theta would be equal to ym over L. This would be the tangent, but again, we can approximate that by just saying it's basically theta. So if this is the angle, the mth bright fringe, we can say that we can say ym over L is approximately m lambda over d, rearrange, and get that on the screen for a typical lab setup. The vertical position of the Wythe fringe is approximately m lambda L over d. In both these cases, remember, m is just a number. We start counting from 0, 1, 2, 3, and so forth, just like we were doing with sound waves. So this m here gets called the order of the fringe. And this is telling us where the bright fringes are located. If you want the dark spots, they're exactly between the bright fringes, and that's how you would go ahead and find them. So just to get some feel for how this works, let's say, just to make this concrete, let's say that our two slits are 50 microns apart, or 50 micrometers. So that is the lowercase Greek mu. So using the special paper that we were all using in elementary school, you draw a mu like that. This is red micro. and it means times 10 to the negative 6. So a millionth. So this is 50 millionths of a meter. So let's say that's 50 microns. The micrometer in English often gets called a micron. And let's just say, again, a very typical wavelength of light is 500 nanometers. So let's say we're using a 500 nanometer laser. So let's figure out what would be the angle in radians of the second bright fringe off of the central maximum. And then we'll also do it in degrees just for good measure. All right. So we can say that theta m is equal to, we can basically say equal m lambda over d. Okay, so in this case here, my m is 2 because I want the second order fringe. My lambda is 500 nanometers. Now, we got to be careful here. Nano, remember, means times 10 to the negative 9. So we need to get this, probably put them both into meters. So to do that, my lambda will be 500 times 10 to the negative 9 meters. And my slit spacing here is going to be 50 times 10 to the negative 6 meters, because remember the micro prefix means times 10 to the negative 6. All right, so we can go ahead, we can multiply top and bottom by 1,000,000 to get, so that gets rid of the 10 to the negative 3. 10 to the negative 6 there leaves behind a 10 to the negative 3. We can cancel a 0. We can cancel the 5 down to a 1. So we have 10 times, so this is what we're left with here is 2 times 10 times 10 to the negative 3. And that's it. The meters cancel. So that's 10 to the negative 2. And since, remember, radians have no physical dimension, we just write RAD just to remind ourselves what we're dealing with. So it's 0.02 radians. So yeah, that's not a very big angle. Let's just express what that is in degrees just to get some feel for that. So we remember that there are 180 degrees in pi radians. So we can take 0.02 times it by 180 divided by pi. And be left with about, 1.14 degrees. So, like I say, typical lab setups, our angles are only ever going to be a handful of degrees. All right, so just to test that thought out a little further, let me bring back this image we had where I was shining red light on the slits. And this is the interference pattern that we get from it. Now imagine that I changed my light source from red to blue. In practice, when I did this, I used a white light source and I had filters that did a very good job of picking out just a narrow band of wavelengths. So here, this is red light, fairly long wavelengths of light. Blue light is shorter wavelengths of light. So I want you to predict what will happen to the spacing of the fringes when I change from red to blue. So go ahead, pause the video, make your prediction, and then when you're ready, go ahead and resume. Okay, so we end up getting this when we switch out the light source to blue light, and you can see that the spacing of the fringes got closer together. If we follow this through, we can see that the angle of the light, the angle of the fringes, is proportional to the wavelength. So if I go to shorter wavelength light like blue, the angles between each of the fringes gets narrower. I can also change the angle by varying the slit separation for the same wavelength. If I make the slit separation wider, the spacing gets narrower. If I make the slit separation closer, the spacing gets wider. So this is pretty much what historically settled the wave particle debate until it got reopened in the 20th century. Young built this experiment, measured the wavelengths of light, saw a wave-like pattern, exactly the same kind of thing that you would see for sound waves. And so, yeah, it was all pretty much thought to be settled until, as we'll see much later in this series of videos, that we had to reopen the question a bit with the advent of modern physics. Alrighty then. So with that, we will continue our exploration of wave optics in the next one. Catch you later.